Hi, Professor. Can you hear me? I can't hear you.
Can you hear us? You can hear fine? I can't hear anything on your end.
How about now?
There we go.
We can.
Okay. All right. Well, my microphone's not doing a darn thing. I was having that problem earlier when the first student logged in, so I thought something might be up, but I figured it was that the student had left, but it was not. It was I was talking to myself. So, anyways, anybody have any questions before we get started? Sorry about that little delay and audio problem.
I had a question, but it could wait till the end of class.
Okay, no problem.
Okay.
So we have started into chapter 27, which was about magnetism in general. And then the next chapter will start into a whole nother set of equations where we're going to introduce Ampere's law and the law of Biot-Savart. Biot-Savart is like it's like Coulomb's law, but like really a horrible version of it because it's got like an integral Gauss product in the integral. And then, like Gauss's law was an easier representation of Coulomb's law, we have Ampere's law, which is an easier representation of uh, the law of Biot-Savart. Of course, just like Gauss's law was limited to certain symmetries, planar, cylindrical, and spherical, we're going to have certain symmetries that are necessary for us to be able to easily apply Ampere's law. Again, it's still Ampere's law. It's not Ampere's helpful hint that sometimes work, uh, but like I said, to use it the way we're using it, which is to solve for the magnetic field inside of an integrand, then you have to have certain symmetries. So let's go ahead and get started. I wanted to make sure you guys are up to speed on the right-hand rule. So I've made up a few simple examples. So let's start off by saying, consider a positively charged particle. So I'm going to share my screen so y'all can read it in real time as well. So now we're sharing. Okay. So with this one, I'm pretty much going to use one drawing for the actual distances, if you will, or for the axes, if you will, for all these problems. But I'm going to imagine that this is due north. And of course, this would be due east. This would be due west. Oh, excuse me. I said west and I wrote west, but I meant south. I was jumping ahead to my next thought, which is west. Okay. And then, of course, this right here is up. And obviously this down here is down. So we look at example one. It says, consider a positively charged particle. So you can pretend this is like a proton traveling northward horizontally, okay, on Earth where there is a magnetic field pointing downward. In which direction will the magnetic force act on the particle? And it seems I forgot to cross my T and multiple instances. So let me fix that. All
Chris,
right.
are you sharing your screen?
What's that now?
Are you sharing your screen?
Yeah, you're not seeing it?
I am not.
Anybody else seeing it?
I can see it.
I can see it.
Okay, so
Just me. Okay.
okay, you got it now, John?
No, I don't. I'll figure it out.
Yeah, see if you can log out and log back in. Everything's being caught on recording, so you won't miss anything. But thank you.
I see it now. I got it.
Okay, cool.
I got it. I'm good.
Is there something that I did funny? Is that why it didn't show up? Anything you can tell?
It was something I did.
Oh, okay, cool. As long as it wasn't me, because I don't mind it being me. It's just a matter of then I have to learn something to figure out so I don't have to do it again. All right, so everybody sees that I have a north, south, east, west diagram down on the bottom left of the page. What we have in this first example is a positive particle moving northward, like this way. That is the velocity, and it's a positive particle. So what we're making use of, by the way, is F is equal to QV cross B, which we talked about somewhat ad nauseum last time, I am going to say, let's get a different color from a magnetic field. I'm going to say the magnetic field direction is downward like this. So what we need to do is use our right-hand rule, and one of the ones that I showed you was QV can point in the direction of your index finger. And since this is a positive particle, V and QV point in the same direction, so they're pointing north. Okay, so north for me, literally in my house is, well, it's actually a little bit that way, but still pretty close to that. And then the magnetic field, which is the second vector in the cross product, has to be represented by this by this middle finger. So if north is this way and QV is this way, my index finger should point that way. But with the magnetic field down, I have to point it this way. Before I decided what the magnetic field direction was, all these different directions were fine as long as this was along the north. But now that I've got downward as that, what I see is clearly this is going to be anyone?
West.
West is what you got. Good job. West it is. So I'm going to circle that off on here. Okay. Let's try another one that says a positive particle headed horizontally eastward and downward. So actually I can take, well, I don't want to undo that. I'll just leave the diagram. I've got that diagram set up for obviously example 1, but you can sort of figure it out for example 2, make your own diagram or whatever. I'm going to do it right here. So this one, it says a positive particle headed horizontally eastward with the magnetic field pointing downward. Which direction is the magnetic force? So now eastward for me is this way, but again, I have the downward magnetic field. So I see that now this finger is sort of pointing towards the screen, which is the northward direction. So does everybody agree with me that that one should be north?
Yeah.
Okay. All right, you guys go ahead and try to do example 3 real quick, and I'll do example 3 without the narration and see if you can get it. Now, remember, this one's a negative particle, so you've got to take a slightly different tact on this one. All right, remember this one is a negative particle headed horizontally eastward with the magnetic field pointing downward, and we want to know which direction is the magnetic force act. Anybody have an answer on that? Here's what I got.
Is it going south?
Good job. Yep, I got south as well. Does that make sense to everyone? This is the time where you definitely need to let me know if you're not getting it, because this is something we normally don't take that much time doing, but I definitely want to make sure everybody gets it. So let's try this one now. This is a negative particle headed horizontally southward with, again, the magnetic field downward. So what are you thinking now?
Is it west?
So yeah, this particle's actually headed southward. So when I do that way, I point this down, this one appears to be, oh, that's right, it's headed southward, so it's that way because it's a negative particle. Yes, westward is right. Good job. All right, any questions on that? All right, so that's how that process goes. That's just something you should be able to do. It's something hopefully you already knew it to some extent just from your pre-calculus or trig class. So now we're going to do example 5. It says an electron is moving from the point 341 toward the point 912.2, and it's moving at 4 times 10 to the 5th meters per second in a magnetic field that is 1 Tesla I hat plus 3 Tesla 4 hat plus 0.500 Tesla K hat. That's a really strong magnetic field and very unlikely to just be loose in an open area, especially not an open area on the order of 6 meters long. But anyways, we're going to go with it like it exists. And I'm asking you to calculate the magnetic force. So the solution here is just going to involve that same equation. But since you guys are, old hat at vector calculus and vector algebra, I'm taking some liberties by really making this a little bit more advanced problem where you actually have to figure out some vectors and stuff like that. So normally I'd start with something a little easier, but I've already done all that easy stuff in the past, so I'm hoping this will work. But the equation we're using is F is equal to QV cross B. Now the electron charge is negative 1.602 times 10 to the negative 19th coulombs. The electron velocity, we know its magnitude, but I got to figure out its direction. Okay. So if you have a vector that points from one point to the other, then you can take final point coordinates minus initial point coordinates, and that literally makes a vector. So what I'm going to do is final point minus initial point. And when I do that, I'm going to get 9.00 minus 3.00. Notice how I'm just subtracting the x minus the x. And I'm going to put it in a less than greater than bracket because that's another bracket for vectors. It turns out when you subtract one point from another point, you actually are creating a vector. So that's just fine. I put the units outside so I wouldn't have to write them twice. Next, I'm going to do 12.00 minus 4.00. Again, putting the units outside. And then I'm going to do 2.00 minus 1.00. Again, units outside. That gives me a vector that's equal to 9 minus 3 is 6. So that's going to be 6.00 meters. 12 minus 4 is 8. So that's going to be 8.00 meters. And 2 minus 1 is going to be 1.00 meters. And that is actually parallel to V. So the ideal scenario is I would like to just multiply it by the magnitude, and that would be great. But however, the magnitude of this vector is not 1. So if you multiply the magnitude of this vector time, or if you multiply this vector times the magnitude of velocity, you're going to not get the proper magnitude. So what we normally do is we create a unit vector, and the way you create a unit vector is you take the vector and you compute its magnitude, and then you divide each component or the vector itself by that magnitude. I can see, for instance, let's call this vector Fi. So this vector Fi has a magnitude equal to the square root of 36.00 squared, or excuse me, that's already been squared, meters squared plus 64.00 meters squared plus 1.00 meters squared. So that should be the square root of 101. So when I compute that, I get square root 101. Everybody agree with my arithmetic on that? Because you know me. So that gives me like 10.05. Whoa. Equals 10.05 meters, which is really, really close to 10.00. And in fact, 36 is 6 times 6. So that should actually give you 3 sig figs. So actually, this is not a sig fig. That's not a sig fig. And that's not a sig fig. Or actually, at least that first one's not a sig fig. When I do 8 times 8, that's 64. So that's not a sig fig. When I do 1 times 1, that's just 1. So that one actually is a sig fig. But when I go to add them, then this no longer becomes a sig fig. So 10.05 meters is essentially 10.0 without the 5. But in doing so, I would be rounding it to the proper number of decimal places instead of 1 extra. So I'm going to keep the extra. And that means that the unit vector for Fi, which I just write like this, remember, whenever you put a hat over a vector, that little symbol I just drew, that means it's a unit vector. So in this case, the unit vector would be 6.00 over 10.05. And notice, not only is it a unit vector, it's literally a unit vector, because when I divide 6 meters by 10.05 meters, I get no units. So it's literally a unit vector. This one will be 8.00 over 10.05, and this one will be 1.00 over 10.05. Again, 1 extra digit on all that. I can go ahead and carry that out and do 6 divided by 10.05. That's going to give me 0.597. And that's only 3 sig figs, so I'm going to call it 5970. The other one, 8 divided by 10.05, that gives me 0.7960. Okay, and 1 divided by 10.05 gives me 0.09950. So that's the unit vector. Now that means the velocity vector is just the 4.00 times 10 to the 5th meters per second times 0.5978 or 70, excuse me, 0.7960 and 0.09950, which should be 4 times 0.5970 is 2.388. For the first component, 0.796 times 4. I'm going to make out all this times 10 to the 5th. That's why I'm just doing the 4 right now. That gives me 3.184. 1 decimal there, 1 decimal there, and 0.0995 times 4. That gives me 0.398. Times 10 to the 5th meters per second is the velocity. Okay. Now what I need is this information on the next page. So what I'm going to do is copy all of this stuff and just paste it on the next page. Copy. Paste. Okay. So you can see there's a lot of stuff on there that I didn't really need. I'm going to go ahead and erase a little bit of that right now. So let's start off by erasing this, because clearly we didn't need it. Didn't need that either. Didn't need that either. In fact, all we really needed was that vector for the magnetic field, and then the vector for the velocity. So I'm going to go ahead and erase all of this, because we've got all that on the previous page. And now I'm going to move all this. Okay. So we now have that. So what I'm going to do is I'm going to calculate QV cross B. So for starters, let's calculate QV. So QV is equal to negative 1.6. I think that's good enough. I don't really need the 602. I'm going to say 1.60 times 10, 1.602 times 10 to the negative 19th coulombs times 0.597 0.7960. Oops, nope, those are not the numbers I'm calculating. Sorry about that. It's 2.388, 3.184, and 0.398 times 10 to the 5th. So this can equal negative 1.602 times 2.388. That's going to give me negative 3.826. And this is actually going to have units of Coulomb meters per second, but I'm going to go ahead and leave that off for right now. Oh, crap. 3.184 times negative 1.6. And actually, I was only supposed to do that last one times 1.6. I'll fix that as well. So this one's 5.0, negative 5.094, and then 0.398 times 1.60. And that's going to be a negative, of course. Okay, 0.398 times negative 1.60. That gives me, whoa, Nelly, 0.63, negative 0.6368. Okay, so that's an extra digit there. And then, of course, that just took into account, actually, let me fix the 0.39, the 3.826. What I should have done is 1.60 times negative 2.388. That gave me 3.821. So that actually does make it a little better, 3.821. So I'm just going to change this. Not significantly better, but a little bit better. And then, of course, 10 to the negative 19th times 10 to the 5th would be 10 to the negative 14th. So this is going to be times 10 to the negative 14th coulombs meters per second. That's the whole units of QV. Okay. So what we now need to do is calculate F, which is QV cross B. Well, the way we do it in here is we take a determinant of a matrix, and the QV is the actual second vector. So I'm going to write that down because that sort of defines how big the spaces need to be. So I'm going to write negative 3.821. And then I'm going to write negative 5.094. And then I'm going to write negative 0.6368. And all this times 10 to the negative 14 Coulomb meters per second. I'm going to put an I hat up here, a J hat up here, and a K hat up here. And now I'm going to take my 1.00, 3.00, and 0.500 Tesla and put that in there. I'll pretty much ignore the units and the 10 to the negative 14th right now. But here's how we do it. First off, I'm going to say the I hat. Now, when you do expand upon the I hat, that means you hide that row and that column. And then, of course, the I hat has the identifiers that it's in the first row and first column. And that is I, j equals 1, 1, which means -1 to the I plus j is just equal to 1. Okay, so for that reason, I just do a regular determinant on the what's left. So I'm going to do negative 5.094 times 0.5 minus parentheses negative 0.6368 times 3, and that gives me negative, oops, that gives me negative 0.6366 for the I component. Then I'll say plus j hat. Now with this one, you can see how this stuff gets really messy if you're actually marking it to do determinants and whatnot. So I'm going to try to erase it now, and hopefully I'll get it from there on out. So now with the j, I am actually hiding the middle row and the top, or excuse me, the middle column and the top row. So that just leaves the negative 3.821, 1.00, and the negative 0.6368 and the 0.5. Oops. So that's the part that's left. But in this case, it's 1, 2. And of course, 1, 2 means that the -1 to the 3 power would be negative. So I actually do the determinant in the opposite order when I do this one, and that corrects for the negative sign. So I'm going to take negative 0.6368 times 1, and then subtract from it parentheses negative 3.821 times 0.5 close parentheses, and that gives me a positive 1.274. Okay, and then I can do the k hat. This time I'm doing the top row and the third column. Actually, I said that was 2 there. It was actually supposed to be a I actually said it was 2, but it was supposed to be a 2, and I only wrote a 1 there. This one's 1, 3, but again, we're back to -1 to the I plus j power actually gives me a positive 1. So I just ignore that third column, and I just do the determinant from negative 3.821 times 3 minus the other one. So when I do this, I'm going to say, dang it, I keep doing that. So I'm going to say negative 3.821 times 0.5 minus parenthesis, not 0.5, times 3. Sorry about that. So negative 3.821 times 3 minus parenthesis negative 5.094 times 1 close parenthesis. That gives me a negative 6.369, like that. And all of this, of course, remember each of these numbers had the not only did it have the velocity as one of the multipliers, but it also had the magnetic field as one of the multipliers. So that means we're going to get all of this, the whole darn thing is going to be times 10 to the negative 14th coulombs, meters, Tesla per second, because coulomb meters per second is what the middle row would be, and then the Tesla is what the third row would be. So that gives you all those units. If you actually worked it out, you'd find that that is in fact the units of newtons. So that works out pretty well as well. So I can finally say that my answer would be F is equal to negative, I darn it, Everything's disappearing. There you go. Oop. Our answer will be negative 0.637 times 10 to the negative 14th newtons I hat plus 1.27 times 10 to the negative 14th newtons J hat minus 6.37 times 10 to the negative 14th newtons K hat. Anybody have any questions on that? So that's kind of like the worst case scenario if you're trying to work out a QV cross B type problem. When you actually have to make the vectors from scratch, that makes it really hard. Ideally, you'd like questions like the ones I asked before, and those questions were just ones where everything was at 90 degrees to each other, and they were very specific directions like north, up, down, south, west, that kind of stuff. So that made it a little bit easier. You didn't even have to revert to actually doing a cross product. But the point is, you need to know how to do a cross product, so we have to occasionally assign those. And I made this the mother of all of them by making it a little bit more complicated by just giving 2 points between which the electron's traveling. So and not only that, it's also very, very hard to sort of see what direction this force is, or what direction. Well, I can see easily the direction that the electron's going because I use very specific coordinates. If you notice, it's a 3, 4, 5 triangle. So I use the 3, 4, 5 triangle in the XY plane. So we know we're going along that hypotenuse, but we went from 3, 4, 5 to a much bigger 3, 4, 5. And then I only increased my K by 1 meter instead of by a factor of 3, like I'd been doing from the first 3, 4, 5 to the second 3, 4, 5. So I can sort of see that. But like I said, you'd actually have to make a 3-dimensional plot to see this. But that should be the answer. Did anybody find any errors with my answers? Did I make any calculation errors or anything like that? All right, so that's not supposed to be too terribly hard. Obviously, it's a little bit of work. It's not something that you necessarily want to do a bunch of during a test, but it's certainly something you should be able to do one, say, during a test or a final exam. So just know that that's one of the criteria that you're supposed to leave this course with is the ability to make vectors and then to use vectors to do cross products and dot products and stuff of that sort. So any questions on that before we move on? All right, so let's start another example. That example, for instance, was example 5. Let's do example 6, and I'll do it right here. I'm just going to do it with a diagram. What I'm going to imagine is that we have a magnetic field existing, and it points out of the page, and it's a uniform magnetic field. By me putting these things regularly spaced, that's supposed to indicate that it's a fairly uniform magnetic field, and we can treat it like a magnetic field that's uniform. What I'm going to do is now draw a wire through this. And what we're going to imagine is that the magnetic field only extends out to this dashed line. Okay. And not only that, I'm going to say that this angle right here is 30.0 degrees, that this current pointing this way is equal to 4.00 amps. This magnetic field strength, B, is equal to 1.50 Tesla. And finally, I'm going to say that this length, I'm going to do this in a different color so it's obvious. let's say that this length of the wire from here to here is 3.00 meters. Okay. What I want to find is what's the total force. So going back to my question, what is the magnetic force on the wire? Okay. Solution. So the equation I gave you was DF is equal to IDL cross B. Now, this is wonderful because it handles all scenarios. But the main thing we're looking at here is we got to know what is I and what is DL. DL is supposed to be a vector pointing along the wire, and you can usually make it an infinitesimal length in case the wire is, oddly shaped and curves and all that stuff. This wire is completely straight though, so you really don't have to do that. But with that in mind, I can just say, okay, that's my DL. Okay. And really all we have to do is figure out what is the, magnitude of the electric field and all that good stuff versus all of this other junk. So I have to figure out the current, which I know. I have to figure out the length, which was given to me. And then I have to know the magnetic field. Now, does anybody see how this 30 comes into play, if at all? The 30 degrees, that is. It shouldn't, right? Because really all we care about is the relative direction between the current, which is parallel to DL, and the magnetic field, which is pointing out of the page. So the fact that this current carrying wire lies in the page tells us that they're actually perpendicular. So this equation reverts down to F is equal to, we normally just say Bill sine theta. Okay, F equals Bill. So what I'm going to do is I'm going to say, and that's the actual magnitude, so I should put bars around it. So I'm going to say 1.50 Tesla times 4.00 amps times 3.00 meters times the sine of 90 degrees. Does everybody understand why the theta is 90 degrees here? Anybody have any questions about why the theta is 90 degrees? Looks like everybody's okay with it. Okay. So, and of course the sine of 90 is 1. So I'm going to get 18.0 newtons is the force on that wire. Now the big thing.
I have a question.
Go for it.
I just want to clarify, is it 90 because it's orthogonal, because we're cross product?
It's 90 because the DL is in the page, and so is I. So that's the vector that's relevant for the cross product. Remember, when you're doing a cross product, you're supposed to put the two vectors tail to tail, and then theta is the angle between them. Well, the vector representing IDL is that wire, and then the vector representing B points straight up. So there's a 90-degree angle between them. I'm glad
That
you
makes
asked
sense.
that. I was pretty sure other people had a problem with it as well. So does that make sense?
Yeah, that makes sense.
All right. Now that we have that, can anybody tell me what the direction is? We know the answer is the magnitude of the force is 18 newtons, but now we need to know what direction. So we're going to use our QV, because remember, IDL has exactly the same units. It's IDL is coulombs per second times meters. So you get coulombs meters per second. And QV is coulombs times meters per second. So you get coulombs meters per second. So you can just treat the IDL like the index finger we had before, and we pretend it's conventional current. So the I actually points in the way positive currents or positive charges would be flowing. So we point it up and to the right at that 30-degree angle. Then B has to come out. Anybody have an idea which direction the force would be? You're going to have to use a combination of two or more words like up and to the left, or down and to the right, or down and to the left, or out of the page.
It's
And
down to the right, right?
there you go, down and to
Yeah.
the right. Exactly. So I'm going to say, oops. Hey, does that down and to right as shown. And what I'm going to do is I'm going to draw it using a black vector.
You could do like a 60 degrees below the horizontal.
Exactly. That works as well. You could do 60 degrees like that. Okay. Everybody see that now? So that's not too hard, hopefully. If you actually had a magnetic field where the magnetic field was tilted with respect to the thing, it'd be a little more complicated, but it's just a matter of figuring out what the angle is when you put the magnetic field vector tail to tail with the QV or the IDL vector. So let's try another one. Whoop, don't know how this goes. Oh yeah, this is another problem. Oh, I must have skipped that last one. Okay. Well, let's see this one real quick. Anybody know? It's a nice little break in the process here. So we have a negative particle headed horizontally eastward. That's actually the same one we already did. I think that was supposed to be made southward. Or did I do the southward already? Let's see. Headed eastward. Yeah, this one was supposed to be southward. I guess I just, nope, I did it up there. Okay, so it's done. I don't know how it got copied over to here, so I'm just going to erase it and pretend we never saw it. Oh, it's a magical page. Okay. This is really weird. This one won't even let me erase it. So what I'm going to do is move that page to the trash. Now I'm going to say copy this page. And now I'm going to say paste this page. There you go. Whoa, there it goes again. Why does this page keep popping up? Let's see if it'll erase now. No, it will not. It's there again. Okay. This is getting crazy here. It's there again. I don't even know what's going on here. But anyways, this is some crazy stuff. All right, so I'm going to have another problem here. I apologize for that diversion. Ah, Dennis came back. Okay, we're living in the end times, clearly. We're all going to die. Something's crazy is going on. So let's imagine this scenario. Let's say a rectangular loop hangs from a scale or something like that. And what we want to do is we're going to put a wire loop where part of it's immersed in a magnetic field. So I'm going to draw the wire loop. So let's say the wire loop goes like this. There's a actual battery there. Of course, it's not good to just connect a plain wire to a battery. So I'm going to put a resistor in it just to keep you guys from, sticking your fingers in light sockets and that kind of stuff, which I generally support the idea of experimenting with stuff. But in this case, I'm going to pretend like I'm a safety hawk. So I'm going to be a safety hawk here. And then here's my length of wire all the way back around here, and then all the way back around here. And now I'm going to draw me a magnetic field. And this time I'm going to take my magnetic field and just put it like right here. And it's going to point into the page. Like this. into the page, into the page, and into the page. And I'm going to say it basically extends. You know, magnetic fields extend beyond the edge of the magnet, but not very far. So we're just going to say the magnetic field only extends to there. I am, in fact, going to have a current flowing through it this way. That current, of course, means it's going to go this way and here, this way and here, this way and here, and then it's going to continue back and go back into the battery there. Let's say this current, I don't know if I want to solve for the current or what. Let's say the current is 2.00 amps. Let's say the magnetic field strength. Let's say the magnetic field strength B, which I should put in green actually, so I'll go ahead and put it in green. Let's say B is equal to 1.00 Tesla. And I actually shouldn't draw that vector on it. I'm going to say that this length from here to here is going to be 1.00 meters. And I'm going to say that this length, which actually you've probably figured out does not matter, I'm going to say that 0.20 meters. Okay. So what we got to think is when we're talking about current, it's just like positive charges moving the direction of the current. What I want to know is what is the force on this wire. So what is the net force on the wire loop? Okay. So first off, we're going to attack this little part over here. So I'm going to put a little red charge right here that's positive and going this way. So can someone tell me which direction the force would point as a result of that one? Answers could be right, left, up, down, out of the page, or in the page. So that little piece of wire to the left-hand side there, which direction is the force acting on that one?
It's to the right.
That's what I got as well. So the F for that little part, which I'll just call F sub L for little, points to the right. Now let's attack the other little part, which has the positive particle going up. Which direction is the force for that one?
On the left.
Yep. So you see that one and the other one are actually going to cancel each other out because notice they depend on the current, which is the same. They depend on the length, which is the same. And they depend on the magnetic field, which is the same. So we know that they're all going to cancel each other out, those two forces anyways. The equation I'm using is F equals I L cross B, which would be the version without the differential in it. So we can already tell that those little parts don't matter. Now what we need to figure out is what about that big part at the bottom? Does it matter? So in that case, I'm going to have again a positive charge and it's moving to the right. So which direction is the force going to be there?
Oh, it's up.
Very good. So this is just going to be the total force, in fact. Okay, that's going to be acting up. So we now know what direction it's in. Now it's just a matter of calculating it. So F total should be equal to well, I can do it like I did before, BIL sine theta. We see that the B points into the page and the L points to the right. They're clearly 90 degrees apart. So this is going to be 1.00 Tesla. times 2.00 amps times 1.00 meters times the sine of 90 degrees. And I think you can see that that just works out to be 2.00 newtons. Upward. Everybody agree with that? Anybody have any questions on that one? All right, now I'm going to do a more difficult one, and this page keeps coming back. It's just haunting me. There you go. Okay, so that was another example. That was not example 3. And look, that page done came back. What the heck is going on? It just covered up all the stuff I had written down. What's up with that? Can y'all still read that well enough? It's a nightmare. Okay. Hopefully when I close it and open it back up, it'll be fine. Let's see. This is supposed to be the 4th. I'll kill that one. And now I'm going to open it back up and see if it's stopped misbehaving. Woo! Okay, good. So it did stop misbehaving. I've erased a bunch of pages since then, but oh well. All right, so that was example 6. This one was example 7, just so I can label it. Now I'm going to do example 8. Okay, so what we're going to have here is I'm going to go ahead and draw a arc, a semicircular arc. And it's going to make it a parabola because it does that to me because it hates me. Let's see if I can do it a little better. I'm going to do maybe 3 by 3, something like that. And then by 3, maybe this will help a little bit better. So I'm going to do, nope. No. Okay, so what I'm going to do is I'm going to draw a circle. Good enough. Now, of course, I cannot erase that, but I can undo all that stuff. All right, so it looks like I'm just going to have to draw a circle and then erase half of it and hope for the best. So let's do that. I'm going to draw this guy going up here, up here, up here, up here, like this. That looks like a pretty good circle. Now I'm going to erase half of it. Well, I was tempting to erase half of it. Looks like I erased a little bit more than half, but I'm going to pretend like I didn't. I'm now going to draw a line straight down from here and a line straight down from here. And I am going to immerse this in a magnetic field. So I'm going to pull out my old green magnetic field stuff. I'm going to put a green X there. I'm going to put a green X there and a green X there. And then I'm going to come down and put a green X here, 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 here. So all of this is supposed to be a magnetic field. I know I slipped it up a little bit, but I don't care enough about it to change those last 3 dots. They should have been down one more square, but that's okay. The main thing is I'm pretending this rightmost wire is perfectly vertical. This leftmost wire is perfectly vertical. And in fact, I have a current I equals 2.00 amps going this way. This magnetic field basically is going to extend. Now, actually, I have to erase the stupid green circles now, because otherwise this don't work out right. So I'll put that there, put this here. Now what's happening is this current is coming up to this semicircular arc and then coming back down this way. And now I'm going to draw my 3 magnetic field arrows where they're supposed to be. And what we're going to say is this is the extent of the magnetic field just inside of these green lines. Okay. So the wire actually goes beyond it, but that part definitely doesn't matter whatsoever. What I'm going to tell you is that this length right here is just going to be called L. And this length right here, which is really, that's actually twice R. So I'm going to say this length is 2R. Okay, so I'm using just very similar, very generic symbols. In fact, I won't even, let's actually not even use a specific current. I'm just going to say the current is I. Okay, that way we can work it out in terms of the geometry completely. So the first thing I want to do, and actually that L should go all the way up to here, not there. Sorry about that. So that L is really up to the beginning of the arc, like that. Okay, so what I want to find is what is the total force acting on this wire. So what is the total magnetic, whoa, force on the wire? Okay, so first off, I'm going to do like I did before and imagine what's going on with the straight parts. I wish this thing would stop doing that. Okay. Still ain't figured out how. Of course, I ain't tried, but anyways. All right, so we got the idea is on the right-hand side, this blue wire has a current going up. So we can pretend that's covered by little positive charges going up on the right-hand side. So that means we need to use that Q and that V and the direction of the magnetic field, which by the way has a magnitude of just B, okay? I need to use that to figure out which direction is the force acting on that straight part of the wire on the right. Can anybody tell me which direction that force is? So we're
It's the
doing,
left.
okay, someone says left, so we got QV going up. B, once I decide that, that's going to nail my hand down. So B actually goes into the page. So yeah, it would be to the left. So in this case, I have F right, which should, for all intents and purposes, be exactly the same magnitude as F left whenever we figure out what that is. So now I've got to do the same thing for the left-hand side. In this case, again, I have a positive particle, but this time its velocity is downward. So what direction is that force acting?
It's to the right. So it cancels out.
Exactly. So this one cancels out again. So I'm going to draw that force on there. That's going to be called F left. So I'm using DF is equal to IDL cross B, right? What I just discovered was, dang it, was FL is equal to FB in magnitude. Therefore, FL plus FB is equal to the zero vector. So we got that handled. That means all I got to do now is figure out the force due to the arc part. Okay. So with the arc part, I'm going to have to switch to some different colors, I suppose. But you might, for instance, consider, let's put the origin right here, say, oops. I'm going to imagine the origin being right at the center of the circle. Call that the y-axis. Call that the x-axis. And then I'm going to imagine a particular part of the actual wire, which is this little part right here. and that little part is going to be DL, okay? And this angle is going to be theta, okay? Now DL could just be written as R d theta, but it points in a very specific direction. In fact, if I blew up this little area, what I'd see is this x-axis, this y-axis, and then I'd see that little arc going by right here, which is at an angle theta, which means if this is the angle theta, then this too is the angle theta. And then perpendicular to that is this little vector DL. Okay, it has to be because it's perpendicular to the radial line. That's the sort of the definition of a circle. Does that make sense to everyone? So if we formed a right triangle with that guy, this angle up here would be theta because this one down here is 90 minus theta. Okay. So we could say that DL is going to actually be magnitude DL times the x component has to be positive and it's going to be a cosine. So it's going to be DL positive cosine theta I hat, or excuse me, j hat. That's the y component. So that's the j hat one. And then the x one's going to be sine theta. It's going to actually be negative. So it's going to be negative DL sine theta. And of course, that one be in the I hat direction, like that. Well, it turns out we actually already know that vector. That vector is actually called, well, if you got rid of the DL, it would be DL times what we call theta hat. That is actually it. Now, the reason why I called it RD theta is because what I'm imagining is I'm going to allow theta to change by an amount d theta, and then according to S is equal to R times theta, then ds, which is equal to dl, is equal to r times d theta. So that's why that's the magnitude of it. That gives you an idea of basically what dl is, and we can actually use that, and we can even use some other vectors, but that one's good enough. So I'm going to go ahead and take that. Now that I have dl, I can go ahead and say f, the vector, is equal to the integral of I dl cross b. Okay, so we've got to actually compute that part. Well, when I go to compute that part, what IDL becomes is, let's go ahead and do this in black. IDL becomes I times R times d theta times what I had for that vector, which is negative sine theta I hat plus cosine theta j hat. That's the vector we just worked out. Okay. So if I think about taking a cross product of that, what I'm going to have is determinant of, in the x component, is going to be I R d theta negative sine theta, and I R d theta cosine theta for the y, and then 0 for the z. The magnetic field, the way we have it written right now, x and y are in the plane, and if you use your right hand rule on that, I hat cross j hat is supposed to give you k hat. So the magnetic field actually points in the negative z direction. So I'll just put negative b down here, 0 here, 0 here, I hat here, j hat here, k hat here. Now, there's a lot of nice tricks you can do to avoid this stuff, but I'm trying to show you exactly what's going on so that you'll better understand. And then when you try to do the tricks, they'll make more sense. So I'm sort of working out all the details, and then we can regroup and look at how the actual author did it, for instance. So in this case, when I go to do a I hat vector, obviously the I hat vector is going to cause us to cover up the first column and the top row. So that leaves that bottom right. Well, notice that has a 0 in the sides of it, but we can still do it. Everything has an IRD theta in it. So I'm just going to pull that out in front, IRD theta. And then I'm going to say out in front of that is now we can write I hat. And when I do this, I'm going to do oh, actually, I forgot I'd already pulled out the IRD theta. So what I've got left now is cosine negative b cosine theta for that part minus 0 times 0. So that's how we did the determinant of the little 2 by 2 that was left. Now I'm going to do the j hat part. And the j hat part, remember, that's the one with the negative sign. So I have to use the right column and the leftmost column, but go in the backwards order. So I'm going to do 0 times 0 minus. Now I'm going to do negative times negative, which in this case is going to be a positive, obviously. So it'll be positive b sine theta. And then when I do the k hat, notice I've got a 0 in both of those. So that's just going to give me 0 there. So that's just k hat 0 times blah, blah, blah minus blah, blah, blah times 0. So we can see now that all that disappeared. And ultimately what I get for calculating this cross product is negative b times r times I times cosine theta times d theta I hat. Okay, so that's just the this part right here. Now I also have this part over here that I got to do, and that's also a negative b. So I'm going to say negative b I r. In this case, it's sine theta d theta j hat. So that's the end of the cross product. Now notice you're going to be integrating this from theta equals, say, 0 to pi. And I think you can imagine when you do this cross product, the I hat component, basically, when we're at theta equals 0, it's going to get a positive for the cosine theta all the way up to theta equals 90, at which case it becomes 0. And then once you get past that 90, it starts going negative. So you can see that the I hat components are going to cancel each other out. That's part of what your textbook author does, is just realize that. But we don't have to actually realize that up front. We can just work it out. So now I can say f is equal to the integral I dl cross b, which equals the integral of negative b I r cosine theta d theta I hat minus integral b I r sine theta d theta j hat. I can pull out the b, the I, the r, and I'll get negative b times I times r times the integral from theta equals 0 to pi of cosine theta d theta. And then, of course, all that's multiplied by I hat. And then plus, notice I pulled the negative out in front, the integral of sine theta d theta j hat from theta equals 0 to pi. So the derivative of sine is equal to cosine. So the integral of cosine must be sine. So this whole thing's going to become the sine pi minus the sine of 0. And the derivative, or excuse me, the derivative of negative cosine gives you sine. So this must be the integral of negative cosine. So I get negative cosine pi minus negative cosine 0. That's what the ultimate integrals are going to be. So I get negative BIR times, now the sine of pi we know is 0, and the sine of 0 we know is 0. So this whole part right here is just 0, but that's what I said from a symmetry standpoint. You expect the I component for theta equals 0 to pi over 2 is going to be like negative, and then from pi over 2 to pi is going to be the same thing but positive. So those two are just going to cancel out. On the other hand, when we do cosine, cosine starts at pi, so cosine of pi is -1, so this is negative of -1, that'd be +1. And then minus minus would be positive, and the cosine of 0 is 1 as well, so this is just going to be 2. So I ultimately get times 2 times j hat. So 2 times j hat, and in fact the answer should be F total is equal to negative 2BIR j hat. That's it. Easy peasy, right? Okay. Yeah. Yes, no problem, Hannah. All right, so we've got that done. That was the last problem I really wanted to work for you guys. So you're free to go. Hopefully y'all followed that. If not, you can find other examples on it on my YouTube channel. I tried a different way that time. I'm not sure how well it worked versus how well it didn't work, but usually I hinge on the fact that I know spherical and cylindrical coordinates, and sometimes I pull those in, and I actually offer that as part of the teaching at the beginning of the semester. So it might be easier that way, but I'm not really sure. So that's all up to you. Notice this is the same answer that your book does when it does a similar problem. However, with the similar problem, they had, I think it looks like the current was reversed. I'm pulling up the book now. The current was reversed, but but the magnetic field was the same. So they should have got exactly the opposite, which it looks like they got 2IBR and I got negative 2IBR. So it is correct. Make sure you text your name in the chat box first and last, and you guys are free to go. And I will see you all next week. Watch out your email. I might actually make some videos over the weekend. Have a good day. I'm waiting for the last person to leave in case anybody has any questions.
Everyone stay safe during the solar eclipse.
Oh yes, there is an eclipse. We're not in the area to see that much of it, but I think we get to see 87% totality. So yeah, check that out if you get a chance. By the way, you can hold up a colander like a spaghetti strainer, and the little holes will make little images on the surface of the earth or its driveway or parking lot or whatever, and you actually see little circles with bites out of them during the totality. But yeah, never look at the sun.
Hi, everyone. Enjoy their day.
Yeah, thank you. Appreciate you reminding me. Anybody else? I'm going to stop sharing this. Somebody needs it back, then I can just put it up. Mitchell and Micah,
Yeah.
Brianna or Micah. Okay, yeah, Brianna had a question. Let me go ahead and pause it since